Hi, welcome to this talk from the University of Exeter entitled Black Holes and Invisibility Cloaks, What Gravity Can Teach Us About Optics. My name is Dr. Simon Horsley and I'm a lecturer in physics at the University of Exeter. I'm a theoretical physicist, which means I spend most of my time thinking about equations, writing incomprehensible things on blackboards to try and understand how something about how the universe works. Now, despite the fancy title, this lecture is really about waves. Because I'm very interested in waves, this is really what my research is about. And I feel that once you understand a wave, you understand a lot about how the universe works. Remember, electromagnetism is a wave, sound is a wave, all solid objects pretty much carry elastic waves. When gravity gets all excited and two black holes merge or something, then it makes gravitational waves. Waves are everywhere. This talk really is, though, about one kind of wave. And that wave is light. And really what I want to tell you about is how I want to sort of give you some understanding of how light interacts with materials, how we understand how light interacts with materials. Because that's really what I'm interested in when I'm interested in waves. And the thing I want to tell you about is the amazing similarity between how light interacts with the material and how light interacts with gravity. And how if you can understand the similarity, you can actually do some interesting things like start to design invisibility cloaks. Now this talk is split into 4 sections. The first section is how materials bend light. The second section is how gravity bends light. Now we're going to spend most of our time with the first section because once we understood that, then the work's really done, and then we won't need to spend very long on how gravity bends light. And then I want to tell you about this analogy between how light interacts with the material and how light interacts with gravity, and show you that it's more than just an analogy, it's actually something quite deep. And finally I want to ask the question whether invisibility is impossible. I want to show you that it's not impossible, and that you can get some idea of how to make something invisible through understanding this connection between gravity and materials. But to sort of kick things off, I'd like to start by just doing some simple experiments in my kitchen. I've made some jelly here. You can see it's, this is just ordinary jelly, nothing special about it. I made it a bit thicker than usual, but basically ordinary jelly. And here I have a laser pointer. So a laser pointer just produces light, which is a wave. In this case, it's a green laser pointer. So this is a wave of electromagnetism coming out of the end of this laser pointer. This wave has oscillations sort of hundreds of nanometers in size. So it's a very small wave, but it's a wave nonetheless. And it comes out in a little column, and that's what you can see. A little column of waves that travels through space. That's what you can see there. And you can see that the light here is going from the end of the laser pointer through the jelly, where we can see it a bit better because the jelly scatters the light a bit, and then off to the other side of the kitchen. Now, you were probably taught in school, I was taught in school, taught this in school anyway, and I ask this every year, and students always say they were taught this, that light always travels in a straight line, and this seems to pretty much bear that fact out. My light is starting at the laser pointer here, it's going through space. You can't see it in this region, but it's there, you can see, because I put my finger there, the light is there, and it travels through the jelly, and there you go, it's going in a straight line. But this thing about light always travelling in a straight line is just complete rubbish. I mean, light always travels in a straight line when boring things are going on, when nothing interesting is happening. We can very simply demonstrate that light doesn't always go in a straight line using this jelly here. So in the simplest case, I can just show you the law of refraction, which you probably learnt in school, or Snell's law, it might have been called. And you can see that if you just shine the light in at an angle. So if I shine the light into the jelly at an angle, it starts off going in this direction, so a straight line, but then when it hits the jelly, it changes direction and goes in a different direction, so it bends. So light doesn't always go in a straight line. This, going from here and then bending, that is not a straight line. I can show you a slightly more extreme example by playing with this one, which was a sort of quarter sphere of jelly I just cut out. Now this is something, so Snell's law, when you do it in school, you're usually thinking about sort of rectangular objects like this. You don't normally treat sort of curved objects like we have here. It's difficult to make it stay still. But you can see in the curved object, you can actually get the light to follow the curve of the object, and then it really is travelling on a curve. So we shine it into this quarter sphere of jelly. We can see it seems to be bending in a funny way. Let's move the laser pointer to the edge. When we move it to the edge, you see that actually what is happening is it's going all the way around the edge. It's difficult to see on the camera, but you can see it's actually travelling all the way around the edge and coming out here. It's actually coming back in the direction that's opposite to where it started. So the light there is definitely travelling in a curve. Now let's look at the theory for how we understand how light bends when it passes from one material into another. And the best place to start is probably something you've seen before. Now you've probably seen Snell's law before, or the law of refraction. Now here I have some images I took from the internet. Now both of them show the light from a laser pointer. You can see laser pointers are great for demonstrating all of these laws of optics. And on the left we have the beam of a laser pointer going into some lump of crystalline something. Not sure what it is, could be glass, but maybe it's probably denser than glass. It's changing direction. Coming in, changing direction, and changing direction again when it goes out. And on the right we have 3 different colours of laser pointer going from, I presume, air, with probably a little bit of smoke in there, so you can see the beam, and bending as it goes into a fish tank full of water, I assume. Now Snell's law relates the angle at which the light is incident onto the material to the refracted angle, so that the angle of light propagation as it's changed, as it goes into the second material. So let's say the materials have got refractive index N1 and N2. Now, I don't know if anyone ever told you, but the physical meaning of these refractive indices, what they mean is they tell you how much the material has slowed light down compared to empty space. So the speed of light in the material is just given by the speed of light c0, so that would be in empty space and vacuum, as it would be, as it's going, let's say, as you send a light wave off to the moon or Mars or something, it would travel at c0 in empty space, but then divided by the index. So the index, when the index is bigger than 1, it slows light down, so light is going slower. And what Snell's law tells you is it relates the angle relative to the normal to the surface, the incidence angle, to the refractive angle. So theta 1 is related to theta 2 by Snell's law, and Snell's law is the first index times by the sine of the incident angle is equal to the second index, second material, times by the refracted angle. So theta 2. And you might sort of have met this formula before, and it might have just been a thing that you just plugged numbers into. But that's always sort of a disappointing use of a formula. Formula is sort of little beasts with, with tales to tell. So it's good to get a feeling for what this little beast is telling us. So let's rearrange this formula a bit. So we can rearrange it. Divide both sides by n2, and then on the left we're going to have n1 over n2, and divide also both sides by sine theta 1 at the same time. So that's going to be. Let's just rearrange the formula so we can sort of see what it means, what it's telling us. So it tells us the ratio of the refractive indices is related to the ratio of the sines of the angles. Now, just to remind you of what the sine function looks like when you plot it out. So if you plot sine theta against theta, it looks like this. You've probably seen this before. Terrible drawing, but hopefully you get the idea. So at zero angle, its value is 0, pi over 2, or 90 degrees if you prefer. I like all these things to be in terms of pi's and things, but 90 degrees, its maximum is 1, and at pi, or 180 degrees, it goes to 0 again. Now for this law, we only really care about this first bit here, because 0 degrees is when the light is going straight in, it's going straight in that way, and 90 degrees the light would be coming along the surface that way, and you can't go, I can't go anywhere else. These are my options for my incident light. It could also go the other side. I could go this side as well, but that would just give me basically the same thing. So there'll be nothing interesting about going the other way. So just 0 to 90 is all we've got available. So you can see that the function goes from 0 to 1, and is kind of a straight line at the beginning and then sort of flattens off at the top. So now let's see what this formula tells us. Well, if the two refractive indices were the same, well, we wouldn't expect this law to tell us that any bending happens at all. So the two refractive indices were the same. That would be 1 on the left here. And so that would tell us that these two sines must be the same. And so that must mean that the two angles are the same. The only way these can, if we're restricted to this region here between 0 and 90 degrees, the only way these two sine functions could be the same is if θ1 equals θ2. And so that must mean that the light just doesn't bend at all, which is exactly what we expect. Okay, that's if n1 equals n2. Now let's take a different case. Let's imagine that n2 here is really, really big. So it's much, much bigger than n1. Well, then we'd have a small number divided by a big number, and that would be very close to 0. It would be a really small number overall. And the only way this right-hand side here could be a really small number, assuming that θ1 is just some arbitrary angle, is if sine θ2 is very small. And from this graph here, the only way sine θ2 can be small is if we're close to the beginning, when the sine is very small. So that means that if the refractive index is really big of the second material, the light basically just bends and goes normal to the surface afterwards. So it bends a lot, and that's the most it can possibly bend. So that would be n2 is much, much bigger than n1. And so then you can see if my refractive index of the second material is somewhere in the middle, it bends, but it just doesn't quite bend as much as this. It doesn't quite bend to 90 degrees. So that's the sort of message of Snell's law. It's not just a formula for plugging numbers in. It's telling us something about the way the world works, and that's the thing it's telling us. The light likes to bend towards materials with large refractive indices. That's the content of this mathematical equation. But remember that mathematical equations have always got some content. They're telling us something about the way the universe works. Right, so to put it into words, so what Snell's law says, or the law of refraction if you prefer, is that light bends into the material with a higher refractive index. And remember, as we defined at the beginning, a higher refractive index means a lower speed. So light zooms along, and then when it hits the material, it likes to bend into the material where it travels slower. Right, now, like all laws named after famous people, the victors write history. Snell was not the one who discovered Snell's law. He rediscovered it. It was actually discovered 600 odd years before by someone called Ibn Sal, who was an Iraqi physicist. Well, there was no Iraq at the time, a Persian physicist. And he obviously wrote it down in a different language, and it was lost to the European scholars. They didn't know he'd done it, but nowadays we know that he did. He basically understood Snell's law a long time, and the Islamic scholars of the time understood a lot of this optics long before the Europeans later on. But like I say, as all things named after famous people, the famous person did not discover it. Okay, so that's probably what you learnt in school, pretty much. Now, that's fine. So you might learn Snell's law and then decide to use it as this equation that you just plug numbers into. Fine, that's one way to operate. But there's a deeper way to understand this law, and I think a much more interesting way. And it forms the sort of kernel of this talk. So let's go back to what we said before. Now, in this case, when the light is bending into the material, remember, light likes to bend into the material where it travels slower. Right, and remember, this is refractive index n1, refractive index n2 for the two materials. And the speed up here is c0 divided by n1, and the speed down here is c0 divided by n2, so the wave is slowed down in the second material. Now, the other way to understand Snell's law, the deeper way, the one that I like, is that what light is doing, so this is an alternative way to view how nature works. What light is doing is you've got to imagine that all of its future is set out before it. It's not like it wanders along and then it finds something and then goes, oh, when I see this material where I go slower, I should bend into it. You've got to think of it differently. Imagine that all of the light's future is set out before it. And what it's doing is its path is always the one such that it will take the least time. So in this case, imagine it starts from A and finishes at B. And then the point C, which is the point at which it bends, is always the point such that light will take the least time to get from A to B. And this is the deeper way to understand Snell's law, that what light is doing, light is a kind of optimizer. It's sort of an optimizing thing. It's finding the optimal path through the universe such that it's always going to take the least time to get between any 2 points, and it sort of knows where its future is. So like I say, its future is laid out before it. So let's work out what would be the quickest path from A to B. What would be the law that governs what the quickest path is from A to B. Now let's do a little bit of, so I'll just move the N1 over there. Let's do a little bit of trigonometry to figure out what would be the quickest way from A to B. What C should I choose? What position? Where should, because C could be over here, and then what the light would do is it would go over there, and it would be bending at a different angle to get from A to B, Let's rip that out because I'm going to need all the space I can get. Okay. But what C would I have to choose in order for it to be the quickest path between A and B? Right, so let's just add some lengths onto this diagram. So we've got a length here. Okay, and we've got a length here, the distance between A and the surface, and the distance between B and the surface. Now I'll choose those lengths the same. So let's say it doesn't really matter where I start along these two lines. I can start anywhere because they're straight lines after they hit the surface. So I'm going to choose my points such that they're equal distance from the interface. Right, and that distance is L. Okay, and then this distance between A and the point C. Remember, this is what we're going to do. We're going to move C around. So we're going to move C around, and we're going to try and find out the position C, where the point should be, such that the light takes the least time to get from A to B. Right, just to re-emphasize it. So that distance S is the distance between A and the point on the surface where the light hits. So S is the thing we're going to change, and we're going to try and find the value of S such that the light takes the least time to get from A to B. Now let's say that B and A are separated along the x-axis by a distance W. Well, that distance between B and this vertical dashed line is going to be W minus S. You can see W is this total distance here. And subtract off S up here, and it gives us this remaining part at the bottom. Right, so now we have everything we need. So distance 1, well, that's 1 here, and that's 2 here. These are the two bits of the straight line, two straight lines. So the distance 1, well, I'm going to use Pythagoras to work out what that distance is between A and the surface. It's going to be the square root of the sum of the squares of L and S. So it's just going to be L squared plus S squared. Now the second piece of distance, so the part where it travels in the material from C to B, well, same logic applies. It's going to be the square root of the sum of the distances, L squared plus, and then in this case it's W minus S squared, so plus W minus S squared. Right, so they're my two distances, but I want to think about light as taking the least time, so I need to convert these distances into time. So what do? We know that speed equals distance over time. So let's rearrange that formula, times both sides by time, and divide both sides by speed. That means that time equals distance over speed. Okay, so we'll use this one here. So time taken, which is going to be sum of the two times, the time it took to get from A to C, and then the time it took to get from C to B. So let's work out that. So it's the first distance, so using this formula here that I've starred, the first distance divided by the first speed. The first distance is L squared plus S squared. Now the first speed we've written up here. Okay, so I've got to multiply that by N1, divide by C0, whoops, C0, and then I've got the second time taken, so the time taken to get from C to B, so that's the second distance, times divided by the second velocity, so that's L squared plus W minus S squared, times by N2 over C0. So that's the total time it takes, and you can see that changes depending on the value of S. So depending on where I put C on this surface, where the light meets the surface, so I can imagine lots of different ways to get from A to B, and I change how it gets there, so and I can change that way to get from A to B along these two straight lines by just changing S. And you can see as I change S, if I make s bigger and bigger and bigger, this number just becomes absolutely huge. So there's no maximum to this number, this time taken. I can take as long as I like to get from A to B. As you can see, if I decided that actually the way it gets from A to B is it just that C is blooming miles away. It's over here somewhere. It's over here somewhere, or even further away. Then it's going to take forever. I can just take as long as I like to get from A to B. If I vary S, there's no maximum. There's no maximum time, but there could be a smallest time. So there could be a quickest time to get from A to B. So there could be a minimum to the time taken. Now if I call this thing t, the way to find a minimum of something, or a maximum, is differentiate and then set it to 0, if you remember your calculus. If you don't, then, well, okay, look up some calculus. You need it, if you can do physics, and, good luck. I love calculus, it's one of my favourite things, but anyway. So let's differentiate our time with respect to s, and when that's 0, that will be the point. If that's 0, that will be the point where this time is a minimum. So let's differentiate with respect to s. Okay, so the first thing, I remember how to do these differentials because I do them a lot, but you can verify them if you like. Well, maybe you can just do them. So that's the differential of the first quantity here with respect to s, and then n1 over c0, and then we do the second one, so that's going to be s minus w divided by this square root of the sum of the squares, and n2 divided by c0. And remember, if it's going to be a minimum, that's got to be 0. So let's leave ourselves a little note to say we're looking for the minimum. Okay, so what does this equation tell us? Right, this is our equation. This is the equation that if it's true, if we can find the value of s such that this is true, that value of s is the one that makes the light travel the least time from A to B. Right. So the thing to recognise is here, remember, so we've done it. Basically, we just need to, this is our law. This is the law that if light takes the least time to get from A to B, this must be the equation that gives us the value of s. So the value that where this point is on the surface, where the light hits before it changes direction to go to B. Right, so remember that sine is opposite over hypotenuse. So the sine of an angle is the opposite of over the hypotenuse. Now let's look at this quantity here, for example. That one there, on the left there. Well, there's the opposite, and there's the hypotenuse here, along here. So this ratio here is the opposite over the hypotenuse, so it's telling us the sine of this angle here. So this thing here is actually sine theta 1. And this one here, well, it's the same thing. It's theta 2, but you see it's s minus w rather than w minus s, which would be this length here. So that is actually minus the sine of theta 2. So what this equation says is that sine theta 1 times n1 divided by c0 minus sine theta 2 times n2 divided by c0 is 0. And that is the equation for the quickest path. A to B. Let's cancel c0's common to both, so we can cancel that out. Cancel the c0's. Move the sine theta 2 n2 over to the other side. And you've got n1 sine theta 1 equals n2 sine theta 2. Great, wow, cool. So what Snell's law really is, I mean, we could just learn it as a law, but what it really is it's an expression of the fact, I should call it Sar's law, really, shouldn't I? I don't know why I'm perpetuating Snell's law. Anyway, it's an expression of the fact that light is taking the quickest path between A and B. you could, like I said, you could learn it as a law, but you could also think it as a deeper expression of the fact that light is taking an optimum path between 2 points. It's finding the quickest path. Right, so this is actually, this alternative way of understanding Snell's law is known as Fermat's principle. And like I said, Fermat's principle tells us that light travels from A to B, between any 2 points, in the quickest time. And the really beautiful sort of philosophical aspect of this is that you've got to imagine that light knows where it's going. That maybe, we have these ideas of free will and how, we go through the world and there's sort of cause and effect. But imagine actually that it's not like that. That what it really is that the whole of the future and the whole of the history is set out behind us and before us, and that what we are is some sort of giant optimization, and light is one of these, one aspect of this optimization. Light is finding the quickest route through the universe. It's always taking the quickest route because, its future is set out ahead of it. And so what we did is we saw it for Snell's law, that this is one way to work out why light is changing the direction in the way it does. And from this we can see that actually light should travel in some materials not in the sort of piecewise straight lines like it does when it goes from air into jelly or air into glass, but sometimes you can get light really to just follow a curve. And so I have a sort of a prototype experiment here, which will show you that this is how it works. So imagine we're going to do this experiment in a minute. I'm going to show you this experiment in a minute. But imagine the following situation. I take a fish tank, which is here, and I shine a laser pointer into the side of the fish tank. And I'm not going to do it with a fish tank in the experiment because I don't have one here. I have a lot of demijohns for making wine, so we'll use one of those instead. But anyway, imagine you have a fish tank, and then what you do is you fill it with water, and then you add to it a lot of sugar. Actually, it's even better to use golden syrup. So golden syrup is even better than sugar because, it's already sort of syrupy. You don't have to wait for the sugar to dissolve or anything. Anyway, you leave the golden syrup in there for a while and it'll settle to the bottom, but it'll sort of dissolve a bit. And so you'll have this sort of gradation in sweetness going from very sweet at the bottom to very sugary, continually up to being almost pure water at the top. So you'll have this gradient in the refractive index where the refractive index continually changes from being very large at the bottom where there's lots of sugar to very close to just that of water at the top. Sugar actually has quite a high refractive index. So now imagine what light must do when it wants to get from A to B. Well, you could imagine it could take a straight line. So some people might say it takes a straight line. Because if it took a straight line to get from A to B, that would be terrible. Because it has to go through loads of sugar, and it's really slow to go through the sugar, so it's not going to be the quickest path. Alternatively, it could go up into the water where it's faster and then down again. It could do something like that. But that's really far, So it has to do something in between. So here we are back in my kitchen, and now I'm going to do an experiment to show you what I just showed you on the slides, which is that light doesn't take a straight line between 2 points when there's a sort of complicated distribution of material in space. In this case, the distribution of material isn't that complicated. I mean, I've just got a container here, a big glass demijohn, just a big glass vase basically, filled with water, and then a couple of these that I just got from the shop of golden syrup. And then I left that for a day, and it settled out into this gradient. You can sort of see at the bottom it's very dark, and then it sort of gradually gets towards kind of water, just pure water. And then on the right I've just got one filled with water. I put a tiny bit of milk in both of them so you can see the laser pointer a bit better. So let's just look at the boring case first. So the boring case is just the glass jar with only water in. Now within the water and the tiny bit of milk, the light all travels at the same speed. There's no change in the light speed throughout this glass jar, so we expect the quickest point between 2 points, quickest way between 2 points, to be a straight line. And if we shine the laser pointer in, sure enough, you can see that the light coming out at the end of the laser pointer, a little column of waves, is just travelling in a straight line. Doesn't matter where I put it in, it travels in a straight line. Now let's try the other case, the more interesting one, which is this case with the gradient of golden syrup. So at the bottom it's very sweet, mostly golden syrup, and at the top it's mostly water. And so at the top, well, we can expect the light to go in pretty much a straight line, which is what we see, because it's just water, and if it was to go down anywhere towards the golden circle and follow some sort of curved path, that would be too slow. So the quickest way is a straight line. But as we go towards the bottom, so if we move this slowly towards the bottom, we should start to see that the light doesn't follow a straight line anymore, and there we go. See, now it's following a curve. In fact, you can see that the light is now not going to the other side of the room, but is now bending so that it hits the table. You can see the dot where it hits the table. And so now you've got to imagine in this funny way that the light is going from A, which is the laser pointer, to B, which is the point on the table, and it sort of knows it has to get there. This is what it was always going to do, and the quickest way through space is to take this funny curved path. Now we want to move on to the part of the talk where we talk about how you can bend light with gravity. Now, you might not have appreciated that you can bend light with gravity, but you can, and this is one of Einstein's main contributions to science, the theory of general relativity, which is the theory we now use to understand how gravity bends light. Now, to kick things off, I just want to show you a little video of, well, you can see it. It's a man doing a spacewalk outside of the shuttle. This is from quite a long time ago. But the interesting thing to take from this video is think about how heavy the man is compared to the shuttle. Now, the man is much, much lighter than the shuttle. But let's think about this. The man and the shuttle are pretty much staying the same distance apart. You can see there that they're staying pretty much the same distance apart. But what are they doing? They're in orbit around the Earth. So the Earth, being a very heavy object, is pulling them down, and they're whizzing around it. You may have done circular motion in school. So being pulled in to keep this circling motion around the Earth. But the weird thing about gravity is that it affects all objects in the same way. So even though the shuttle is so much heavier than the man, the shuttle is pulled on exactly the same course, and so they orbit around the Earth together. So the remarkable thing about gravity, again, is that it affects everything in the same way. And so this is just a little diagram to show this. So what I've done is I've drawn time. This is distance here. And I've imagined that two objects have been placed some distance outside the sun. So the two objects I've chosen here are the space shuttle and the man. And imagine you drop them into the sun. Horrible thing to do, but let's say we do it. And so we wait. You know, this is time 0 down here when I let them go, and then I wait some time, and then if I look, well, okay, they've ended up here, so they're at this distance, and then some later time, they're here, so this distance, later time again, they're here, so they're this distance. So as time goes on, you're getting closer, ever closer into the sun, accelerating into the sun. And the weird thing about gravity is that both the shuttle and the man, despite the fact that one is much heavier than the other, would follow exactly the same path. This is the strange thing about gravity. It doesn't matter what the object is, how heavy it is, it will follow the same path under the influence of a gravitational field. It will be accelerated in the same way, is what I'm trying to say. So it doesn't matter whether I drop the man, or the space shuttle, or the moon, or Donald Trump, or an atom. All these things will take have exactly the same acceleration in the gravitational field, and so if I drop them from outside, they will follow exactly the same path. Now, this is the thing that Albert Einstein recognised. He recognised that everything would follow exactly the same path in the gravitational field if they were started in the same place. So they would have exactly the same acceleration. So his idea was, well, let's not think about gravity as a force like we normally do. Let's think about it as some interaction between two objects, some kind of force between two objects. Let's instead think of it as some sort of distortion of space and time, some change in the way that clocks tick and change in the length of rulers. So the change in the length of things, and maybe that's why things move in a strange way in a gravitational field. And so to put it, so for the simplest case, like we have in the case of the sun here, this is a reasonably simple case of gravity. What Einstein's theory of relativity says is that out here clocks tick faster than in here. Time runs more slowly when the gravitational field gets stronger. And that's what his theory of general relativity says. It says instead of thinking of forces, you should think about time passing differently. So time gets slower the stronger the gravitational field is. And just for interest, there's a kind of Fermat's principle that you can use to work out also the path which massive objects take through space and time according to general relativity. So imagine this atom is being dropped into the sun. You can imagine it wants to get from A to B, just like our Fermat's principle earlier, but this is for massive objects, so this is a little bit different. You've got to imagine that that object is carrying a clock with it, and the analogue of Fermat's principle is that that clock must read the biggest value. So if you imagined it carried a clock with it, well, okay, it wouldn't ever want to be very close to the sun because that's when the clock ticks most slowly. So it takes this funny curved path, which is the accelerated path in this case, in order to make the reading of its clock as big as possible. Right, but that's for massive objects. Let's think about light. That's what this talk is about. So let's see what this different way of understanding gravity, what that implies for light. So let's imagine we have light. We have a really heavy object first. And let's say it's a black hole. I said I'd tell you about black holes. So let's say we have a black hole. Again, we have our laser pointer, shining light. And let's say the light wants to get from A to B. So the light is going to go from A to B. Now, the only thing we need to remember is that the clocks close to the black hole will tick slower than outside. In fact, the thing about a black hole that's very interesting is that it's special because it has this thing called an event horizon, which is where from outside clocks appear to be ticking so slowly that actually they've completely stopped. And beyond the event horizon, we don't know. We can't access it. So the clock's ticking slower. What that means is that it means that everything appears to be going, or time appears to be passing more slowly close to the black hole, which means that light would appear to travel more slowly. So if we look at light going from A to B, if it goes in a straight line, this is bad news because it has to go through the black hole, which seems to take a long time. It could, of course, avoid the black hole completely, but then that's too far and that takes ages as well. So just like with the sugar solution, light, again, is bent into this curve, which is some in-between, some optimal path. So it's bent by the black hole in exactly the same way, using exactly the same principle, Fermat's principle, the principle that light should take the least time. It's bent using exactly the same principle, and so gravity has the same effect on light as a material does. The same principle governs the curved path of light in both situations. So let's see some evidence for this. Imagine you're looking out at the night sky. So typically you see clusters of stars, individual stars, you see a supernova if you're very lucky, galaxies. But sometimes when you're looking out into space, people see strange objects. So they use telescopes and they see all sorts of strange things like this here. So imagine this is looking out into space. Well, okay, you recognise everything except probably this thing here. What is that? The thing I've circled, well, it's not circled. What is that weird shaped object there? That is like nothing. I mean, is it some sort of strange partial ring of matter that's sat there? Seems very unlikely. And why is it surrounding this object here? Now the answer is that this object in the middle is very heavy. And what this thing is, this bluish thing that I've put inside this shape here, what that is it's something that's actually behind this very heavy object. And what's happened is it's come from behind the object, and then the light has been bent and lensed, just like a lens bends light in. And this distorts the object and sort of squishes it in. So if the blue object was here, we'll just do a picture from above. So this is the blue object. And then this is the heavy one, the heavy bright one. There. Then if you imagine light coming from the blue one, and then this is the observer with the telescope here, what would the light do? Well, again, it gets bent, just like it does in the refractive index profile we saw earlier. It gets bent inwards. And so what the person would see there is not the blue object as it would ordinarily appear, but the object kind of distorted, and that's what this is. Right, so what I've shown you so far is that there's a great similarity between how light behaves in a gravitational field and how light behaves in a material. Now I want to show you that this is more than just a sort of a fun analogy. There's actually a bit more to it. It's very deep, this connection between gravity and materials. And to sort of make this point, the way I'm going to do it is I'm going to give you a little quiz, because I am a child and I like games like this. So now we'll have a quiz. Right, so the quiz is over. What was the point of all this? Well, the first round of the quiz was reasonably easy, I hope. And the person pictured in that first picture is someone called James Clerk Maxwell. Now, James Clerk Maxwell is responsible for our modern understanding of electromagnetism. That's electricity and magnetism. Now, light is an electromagnetic wave. So Maxwell's equations are the equations that govern how light behaves. And they're the best, probably, well, in my opinion, they're the best set of equations we've got in physics. They just describe so much of how the world works. Now, what we have on this image here are Maxwell's equations, and they're in Maxwell's equations in two cases. On the left-hand side of the vertical line, we have Maxwell's equations in a material. And now, I don't expect you to understand the equations in any sense. So this is stuff you wouldn't learn until you were way into your degree. All of these funny triangles and these bold letters and these funny curly Ds. I wouldn't expect you to learn any of this stuff, know any of this stuff now. I just want you to treat it like Spot the Difference. Now, on the left of the line, we have these red circled quantities, this epsilon, the funny E-looking thing, and mu, the funny sort of U-like thing. And all you have to remember is that, in this case, what these represent is the properties of a material. So these are sort of generalizations of the refractive index. They're the properties of the material, what we've been talking about throughout most of this talk. And on the right of the line, we have Maxwell's equations now, not in a material, but in a gravitational field. Now, the gravitational field has certain properties, and these properties are encoded in this square root of g, and then this bold g with this -1 above it. They are the properties of the gravitational field. And the thing you have to take away from this picture is that gravity appears in exactly the same place as a material does in the equations. Gravity is mathematically equivalent in these equations, these fundamental equations that govern how light works. Gravity is equivalent to a material. They act in exactly the same way upon light. Gravity is a funny kind of material. And that's really the point I want to make. One of the main points I want to make is more than just a fun analogy. In a very deep sense, gravity is a funny kind of material for light. And this is why Fermat's principle applies to both of them, why light ends up taking the quickest path in a gravitational field, just as it does inside a material. They are somehow the same kind of thing. Now, what can we use this knowledge for? Well, in the very last bit of this talk, I want to show you, or explain to you, how this knowledge can be useful for designing invisibility cloaks. Now, what can we do with this knowledge? Well, what I want to quickly show you before we finish is that this knowledge can be applied to design some interesting devices in optics, one of which is an invisibility cloak. This is probably the most famous application of this piece of knowledge. And when you tell people, well, you can design an invisibility cloak, most people say, well, invisibility is impossible. And what I want to show you here, with this sort of silly example, is that invisibility is not impossible. So what do we have here? Well, on the right we have a wine glass, and the wine glass is filled with some what look like little plastic beads. And you can definitely see them, right? You can see them at the moment. Here they are. There are the beads. But let's put them in the water. Watch them fall into the water. Okay, they're invisible. So visibility isn't impossible. And you might think, well, okay, this isn't a very good picture. You filmed this on a phone. This is, not good quality. But let's show you a sort of more extreme case. Let's make them all invisible. There you go. They all disappeared. So invisibility is not impossible. You can make things invisible. Now the way this works is that those small beads, well, what they are is they're a kind of polymer that absorbs water, a lot of water. So it's the same things you put in nappies, actually, the same polymer you put in nappies. And they start off as tiny little beads. You put them in water, and then they get bigger and bigger and bigger as they fill with more and more water. So actually they're mostly water, which means they have the same refractive index as water. So light can't tell the difference between the beads and the water, and therefore it passes through, doesn't bend, doesn't reflect, nothing happens. But this is a kind of rubbish kind of invisibility, because if you think what you'd have to do to make a person invisible the same way, you'd have to make the person have the same refractive index as air. And that would involve vaporising them, presumably, which is a pointless and cruel thing to do to a person. So instead, what I want to show you now is how this knowledge about gravity in a material having the same effect on light, how that can be applied to design a different kind of invisibility cloak, and one that is more practical. What would we need to do to light to make something invisible? Well, let's have a go at that. So imagine we want to make this thing invisible. Imagine this is the thing we want to make invisible. Now why is it that, let's say we've got the person over here. Why is it this person can see the flower? Well, first of all, light reflects from the flower. And that makes you able to see it. And secondly, the light from behind it illuminates it from behind, and you can see light passing through it. So you've got reflection, you've got light reflected and transmitted. And that's why you can see the flower. Light comes from all around, bounces off the flower and goes to your eye. So what you'd need to do to make the thing invisible is you'd need to cover it in something. You need to put something around it, some material around it, so that when, firstly, that material would have to not reflect, and secondly, it would have to be such that when light, let's say, comes in from here, where it's going to hit the flower, it's guided around the flower and then comes out as if it had just gone in a straight line and there'd been nothing there. And this would have to happen for all the light rays. So even one here that's going to hit the flower directly would have to go around somehow the flower and then come out as if nothing had happened. Right, and that's the kind of invisibility cloak I want to talk about. Now, how can we use our analogy, our understanding that gravity is equivalent to material, to do this? I just want to very simply show you how you do this. It's called the theoretical transformation optics, but just draw a grid. So this is my grid. Let's say this is space. This is space. Now, if you were to draw what light would do in this space, okay, there's nothing in it, so it would just go in a straight line. So I want to design a space-time, because remember, gravity is space-time, and space-time for light is equivalent to a kind of funny material. So I want to design a space-time such that there's a hidden region. Well, what can I do? Well, one thing is I could just take a point in the space and I could just let's just tear a hole. So now I've got a new space where there's a hole torn in it. So this is my hole that I've just torn in the space. Imagine it's a fabric that I just tore. And now I stretched out, so what were my rectangular grid lines become these funny sort of curved ones, because I stretched out where the hole was. And then far away it just becomes sort of like it was before. So I stretch a hole in this, I make a hole in this space. So that's my stretching out. And then what light would do in this case is it wouldn't ever be able to go in the hole, because that's not part of the space. So it would be guided around these lines. And that does exactly what you want for an invisibility cloak. So you could design a space by ripping a hole in it, such that there was a hidden region. And that's exactly what you do to design an invisibility cloak. And what you can do is then translate this space with a hole in it, you can then translate it into a material, because remember they're equivalent, and then try and build that material. And people have attempted to do this, so there's a whole field of research that's been going on since about 2006, where people have come up with various designs of invisibility cloaks using mathematical techniques such as this, and then tried to build them in the lab with varying degrees of success. But all I'll say is it does work for many kinds of waves. You can design and build invisibility cloaks this way. So that concludes this lecture. I hope you've enjoyed it. Okay, that's everything. Hope to see you again. Bye!